Okay, any questions? Now, if you remember, when we were discussing these topics before the blackbody radiation, we were talking about some differences between particles and waves. And we had said there that one of the most important differences between these two are the diffraction and interference. Waves satisfy the superposition principle, meaning that if you have two waves, the typical example is the double slit experiment. You send some light into the double slit experiment. On the other side, you have a screen. And you would see that you would have such an intensity pattern on the screen. And we explain this by saying that, okay, if you take an arbitrary point over here, the electric field at that point will be just the sum of the electric field coming from one of the slits, let's call that E1, and the electric field coming from the other slit, let's call this E2. Since E1 and E2, they are both oscillating functions, if this, depending on how much these distances differ, you would have them added constructively. They would have the same sign or different sign. If they have different sign, the sum will have a magnitude smaller than each one of them. If they have the same sign, the sum will have a larger magnitude than each one. So you get this interference pattern. You don't expect this in particles because basically then you are counting the particles. And if we were, instead of sending waves, if we were sending particles, what we would expect is that if there are 5 particles come to this point and 10 particles coming from this slit, then we would have 15 particles over there. We won't have such dips if they were particles. That is what we would expect classically. But now we have discussed two phenomena. One was the blackbody radiation, the other one was the photoelectric effect. And these two phenomena led us to the conclusion that electromagnetic radiation itself is made up of photons, which are particles. Now, what happens to the interference? How can we explain this interference phenomenon in terms of particles? Because if they are made up of photons, then let's say at this point, if 5 photons comes from this slit and 10 photons comes from this slit, then we should have 15 photons there. And the number of photons is a measure of the intensity of light. But we know that from experiment that no light is falling at that point. Now, on one hand, in wave picture, the intensity is proportional to the electric field, let's say average or squared average. You take the square of the electric field and then average it. That is what we call the intensity of light. The light has both electric and magnetic fields, so that's how we would define it. So on one hand, we have this description. On the other hand, we have the intensity is proportional to the number of photons. Now, these two descriptions seem to be contradicting each other, but the way to reconcile them, to have an interpretation, let's say, of both of these apparently contradictory claims is to say that E squared is the probability of having a photon at a given point. Let's say proportional to. Why does this, let's say, this understanding, it kind of reconciles these two descriptions? Because in the particle description, what we now have is, at this point, the probability of observing a photon is much larger. And hence, if you send a very large number of photons, most of them will be falling on this point. But since E squared at this point is almost 0, the probability of having a photon at this point is 0. So no photon reaches that point. No photon goes in that direction. So that will be the way how we interpret this interference pattern in terms of photons. Now we have this new concept of the probabilities for particles. And what is actually interfering over here is the probability waves. You see, since E squared is a probability, E is the wave. So E is called the probability wave. And the probability wave satisfies the superposition principle. And hence, the probability wave interferes. So particles show this interference phenomenon. Well, let me find you some videos. After the publicity. Now, you see, a couple of problems here is, so what happens if we send one photon at a time? Will we see the interference? Well, this is the experiment. You see, the interference appears because we have the waves passing through two different slits. But then we have a single particle, and we tend to think of particles as if they are passing through one slit or the other slit. So if we send one photon at a time, how can we see the interference pattern?
With crests and troughs with troughs. So they add together and create an interference maximum, a bright constructive interference, and so we see a bright spot of light. And that's how the whole pattern is created. But what if I decrease the intensity so much that there wasn't a whole wave of light going through there were only single photons? Then how could they interfere with each other because there's only one in the device at any one time? So would we still see an interference pattern? That is what we're going to find out. In order to make this work, I had to line up a very faint source, and to see where the light was going, I had to shroud my head in that black cloth. But I finally have the apparatus ready. You can see up here I have a frequency counter which actually counts the number of photons received per second at the detector. The detector is a photomultiplier tube, which is capable of detecting single photons. It's like a very sensitive eye, like the frog's eye. Now, right now, there's no light passing through to the detector, but there is still a bit of a background reading, and that's because I can't block all the light out of there. Plus, there are cosmic rays passing through this room, which will also set off the detector. I'm plotting a graph
the black body
of
radiation.
photons counted as a function of position across the detector. If you have a look after 1 second, the distribution seems random. There doesn't seem to be any pattern in the arrangement of those photons as they hit the detector. So maybe it's true. A single photon can't interfere with itself because it's just a localized point. It has to go through one slit or the other. But just to be sure, let's add up the results over a period of time and see if any pattern emerges. Look at that. you can clearly see the same interference pattern that we got when we were sending tons of photons through, but we're getting it out of single photons. We're counting up individual photons. And that pattern is emerging as we aggregate the results over time. But how could this be happening? How could a single photon pass through both slits? Well, if we try to interpret these results in terms of the objects we experience every day, they don't make any sense. A photon is something different to a macroscopic object. It's not a wave and it's not a particle, it's a quantum mechanical object. And sometimes it seems like it has properties of a wave, and sometimes it seems like it has properties of a particle, but ultimately it is something totally different to anything we've experienced before. And that's what makes this seem so counterintuitive. So what is light, wave or particle? The true answer, I think, is neither. Though if you want, you could call it a wavicle. Created by the ripples from the two sources.
Okay, so even if you send the photons one by one, they do interfere. And okay, as he also stated, one thing you have to get used to is avoid asking questions like, does it behave like a particle or does it behave like a wave? When do we know how does it behave? If you given a problem, if you treat your problem properly, your result will tell you how it will behave without you making any assumptions whether it behaves like a wave or a particle. Now, we will see some cases where we will choose one description over the other one and it will give us a good enough approximation. Now, what they do is they have this laser, which is nothing but a photon source. They send one photon at a time. So there is one photon, on the other side there is the detector, and that detector determines where it hit on the screen. Well, this is, let me open that graph. Okay, so what they said at the position, for example, 6.2 millimeters, they have measured approximately 280 photons. And at the positions, let's say around 5.8, they have measured around 120 photons. But they are sending the photons one by one. And this is what they see. Yes. Theoretically, this should be 0, but this is mainly the background photons. You see, all of them have more or less the same value. There are photons in that, within a given frequency range, let's say, there are more or less equal number of photons passing through the apparatus. There are, as he stated, the cosmic rays and the black body radiation, if any. Well, you measure. You put detectors at different points, and you just count how many of those detectors give a signal at a time. If you lower the intensity lower the intensity of the light source to such values, then the number of sensors that signal at the same time gets smaller and smaller. Eventually, at a given time, only one sensor signals. In that case, you know that, you see, these sensors, you can imagine them as, well, like the CCD cameras, your cameras. If there is light falling on them, they just register it. And you see, there you have your sensors over here. You just count how many of them signal a light at a given time. And they lower the intensity to such values that only one of them signals at a given time. Then you know that there is a single photon, and single localized photon. Because this sensor over here just measures a photon coming at this point. And then once you are sure that you are sending a single photon at a given time, then you can just measure how many photons each one of them measure throughout the experiment. You know their position, and then you can create that graph. Somebody from the back? Yes. Well, let's delay those questions until we study uncertainty. What do you mean by uncertainty? You should always be careful whenever you are thinking about physics. You should always be careful about your definitions, like we have seen in the special theory of relativity. First, let's define what we mean by uncertainty, and then we will discuss. Yes?
How do you know that the particle hasn't just applicated in one position?
Hasn't
just collected in one position more, or hasn't just like accumulated in one position more? That's why.
Well, you see, this is the experiment. He has the slits over here. He has the laser source. And he has the sensors as his screen. First, you can start with a high intensity. Then you will know that at a given time, more than one sensor makes a signal, saying that, oh, there's a photon here. Then you lower the intensity such that at a given time, only one of the sensors will signal a photon. Then you know that it's a single photon passing through. And the sensors are just points, very small objects. So you know that the photon has reached this point if this sensor signals. Or if this sensor signals, you know that there's a photon that came to that point. Of course, it's not just the point, it has a width. That is why in this graph also you have this binned structure. Within this distance, this much photons has reached.
Ya bu grafiğin bir açıklaması bir foton kendisinden önce gelen bir fotondan bilgi alıyor olabilir mi? Onu bir de pattern'ı oluşturuyor olabilir mi?
Now we will explain it, but what does it mean to... what about the first photon? Yeah, then you are saying that every photon, well, then you are saying that we have a time travel in a sense. What does that mean? Now, any questions on this wavical property? You see, for the time being, we are only talking about the photons. And photon is something that we thought was a wave, but now it behaves like a particle. Now we will ask the similar question in reverse. If a wave behaves like a particle, can a particle behave like a wave? That will be the opposite question, but that is probably in a couple of weeks. We will start discussing that. Other questions? Now, before we discuss the wave properties of particles, let's discuss some other interactions of waves and particles. Let's look at the X-rays. Now, in the case of the photoelectric effect, what was happening is we have a light source which hits some surface, and if its frequency is large enough, then it starts ripping electrons. Well, some of you were asking, well, does it have to be a metal? No, it doesn't have to be metal. For any material, in fact, it will work. So in fact, because it works, we get cancer from radiation, etc. Anyway, so if we have the light electromagnetic radiation falling on a material, it's ripping off electrons. What about the reverse? If we have electrons, can we create electromagnetic waves? And the way if you have ever had your Röntgen taken, basically you are using that phenomena. We can create X-rays using electrons. So the idea is you have some metal surface, Then here you have an electron gun. Again, they are usually in a cavity, in vacuum. You have an accelerating potential. This is negative, let's say this is positive. So this one is also heated. You see, it doesn't even have to be light to liberate the electrons. If you heat a material, you are, as your friend has pointed out last lecture, basically you are increasing the average energy of the atoms and the electrons. Well, while they are colliding, it might happen that an electron acquires enough energy to overcome the potential barrier. So if you heat a metal enough, it will start emitting electrons. This time, the energy that the electron needs will not be provided from the light, but it will be provided mainly from this thermal motion. So you just heat that electron gun, it liberates the electrons, then you have this accelerating potential. You see, this time it's not the stopping potential, but rather the accelerating potential. So you accelerate the electrons. At various, here, when they are liberated, they have just a couple of electron volts, and an energy of a couple of electron volts. Then you accelerate them. When they reach the target surface, they will have energies. V is typically of the order of tens of kilo-electron volts. So when they reach the other surface, they will have this much energy, and they just emit electromagnetic radiation that we call X-rays. Since their energy is so large, they will be creating dominantly the X-rays. Then, well, you have some electromagnetic radiation over there. You can measure it, measure its properties as a function of, let's say, frequency. How much electromagnetic radiation, how much X-rays you get within a frequency range. And it turns out, let me just look at the graph. For different materials, you have such graphs. This is tungsten at 35 keV. And this is molybdenum, different materials. Again, 35 keV. Or you can have a single material and bombard it with electrons and electrons at different frequency, and you get these graphs. Let's say for 20 keV, 20 kilovolts. Sorry, these are kilovolts. Then if you increase and this, the highest one is 50 kilovolts. So if you accelerate the electron through 50 kilovolts, you get a larger intensity. But you see, if you look at the frequency, again, you get a similar feature as in the case of the photoelectric effect. Independent of the material, there is a minimum frequency. So these are not as a function of frequency, but rather wavelength. This is lambda. Well, there is a maximum frequency you have. You basically get all the frequencies up to a maximum frequency. And that maximum frequency just turns out to be independent of the material, but it depends on the energy of the electrons. Now, in this particle nature of the electromagnetic radiation, that feature is easy to understand. You see, you have the electrons they have a kinetic energy. And then when you send it, part of that kinetic energy will go into radiation, electromagnetic radiation. And part of it will still be the remaining kinetic energy of the electron. Now that electromagnetic radiation, it has an energy h nu. So the maximum value of h nu is nothing but the kinetic energy of the electrons. But the kinetic energy of the electrons is nothing but E times V. Their charge is E. They are accelerating through a voltage of V. So this is the maximum kinetic energy. Maximum kinetic energy. So we know what nu max is. This is just EV over H. So this is C over lambda min. So this tells me that the minimum wavelength would be just HC over E times 1 over V. In fact, that was determined first experimentally. And the coefficient of 1 over V, if you look at the upper graph, the larger the V, the smaller the lambda. So lambda just decreases inversely with the voltage. And before you ask, well, will that behavior can be extended to V is equal to 0? No, not really. You see, here we made a couple of approximations. One approximation was that here we have the electrons. When the electron enters the metal, its energy increases, its kinetic energy, because of the potential difference. But that potential difference that we call the work function is just a couple of electron volts at most. But the energy of these electrons, usually the potential is at the order of tens of keV. Well, a couple of electrons you can just ignore compared to these tens of kilo electrons. Are these electrons moving at relativistic speeds, by the way?
Exactly C or close to C? Exactly C or close to C?
Close to C, comparable to C.
So they move faster than light in the material.
Do they?
Not the C, the light speed in the material.
Okay, do they?
They may, or but they.
How do you determine that?
According to us, I mean, not just the electron, in our reference.
In our, I mean, we are in the lab, we are talking in the lab reference frame, unless we state it otherwise. How can you determine whether something is moving at relativistic speeds or not? How? Just estimate. I mean, you have all the numbers, right? Do you know the mass energy of an electron? For electron, me times c squared, this is something like around 0.5 MeV, or 500 kiloelectron volt. So if you accelerate an electron through a potential difference of 500 volts, then its kinetic energy becomes comparable to its rest mass energy. Then you know that it is relativistic. You see, the speed of an object, v over c, do you remember its expression in terms of its momentum? It's p over e, pc over e, or square root of e squared minus mc squared squared over e. Or if you write E as kinetic energy plus mc squared, this becomes kinetic energy squared plus twice its kinetic energy times mc squared divided by E plus mc squared. So if its kinetic energy is comparable to mc squared, then this ratio will turn out to be something close to 1. Now these electrons, let's say 35, accelerated through 35 kV, kilovolts. Well, the mass is 500 kilovolts. It's not highly relativistic, but still it's not moving slow. It's quite something fast. Now, there is the question, okay, we say that if we create such a system, there will be some electromagnetic radiation emitted. How do we know that they are X-rays? How do we measure their wavelength? You see, the energy of these X-rays will be typically of the order of 10 kiloelectron volt. What is their wavelength? How can you determine their wavelength if you know the energy? Divided by? You see, h nu should be 10 keV, which tells me that nu should be 10 kiloelectron volts divided by the Planck's constant. What's the Planck's constant? Well, let's see, this is approximately 10 to the 4 times 1.6 times 10 to the power minus 19 joules divided by Planck's constant is 6.6 times 10 to the power minus 34 joule seconds. So this is approximately 1 over 5 times 10 to the power 11 hertz. Or let's say this is approximately 10 to the power 10 hertz nu. What is the corresponding wavelength? C over nu. C is, this is approximately 3 times 10 to the power 8 meters per second. Nu is 10 to the power 10 per second. No, sorry, I made a mistake over there. This is 34 minus 19 is 19 hertz. So 10 to the power 18. 10 to the power 18 per second. Per seconds just goes away. So this is 10 to the power minus 10 meters. So how do you determine the wavelength of an electromagnetic radiation? How can you determine the wavelength of an electromagnetic radiation? Of light? Well, the easiest way would be the interference. You do the double slit experiment. And then we said that on the other side you would see all these peaks. On one hand, you need to have, let's call this L1. If this is L2, then L1 minus L2 is just wavelength over 2. So if you do this experiment and measures this length, well, if you measure, you see the first peak, first dip, and then you measure the distance of that dip from your slits. If that difference, the distance of those lengths is just half a wavelength, Well, it should be half a wavelength up to the first dip. So basically, if L1 might be such that here, let's say you fit 5 complete wavelengths, then in L2 you don't fit 5 complete wavelengths, but 4 complete wavelengths and a half wavelength. But if you only fit half a complete 4, let me just plot them. You see, this is 1, 2, 3, 4, and 5. Let's say this is all of your L1. If in L2 you just have half a wavelength up to here, let's say, 1, 2, 3, 4, 4. Let's just assume you are leaving from here. And this point reaches the screen at the same time. But if you keep adding them up, no, this is wrong, sorry. Okay, on the other one, you have a half a wavelength. So essentially, the other wave comes like this to the other side. So you see, one of them is now increasing, the other one is decreasing. So at this point, these are the same points, they will just add up to 0. One will have positive values, the other one will have negative values. So you get essentially 0 intensity at this point, if the difference is half a wavelength. But now, if you want to measure the wavelength of this wave, well, the distances you need to measure will be of the order of 10 to the power minus 10. And also keep in mind that this pattern, you see, all of this pattern has a width, which is more or less the splitting between these two slits. So if you want to see anything of this sort, you need to have slits that are separated by a distance of 10 to the power minus 10 meters. Well, you cannot just cut these slits. Any idea how you can create these slits? Or any idea where you can find such slits? Exactly. Basically, crystallography. If you take a crystal, it's just a evenly spaced. Well, this is a very simple cubic crystal. For example, table salt has such a crystal structure made up of 2 different atoms, sodium and chloride atoms. This is a lattice structure. Well, this is as I said, it's just a cubic lattice. You can get more complicated lattice structures. Now, let's say that you send some X-rays. Well, see, here, each one of these atoms, let's say, they are not really actually point-like, but they have some finite volume. The separation between those 2 points will be typically of the size of the atom, which is 10 to the power minus 10 meters typically. So now here we have many slits, not just the double slits. So if you arrange your system such that, let's say, you send some X-rays in this direction, and some of them will be reflected from this surface, And then some other ones will just pass through and will be reflected from the next layer. Let's say this is theta. This distance between two layers, let's call it d. Now, if you put a detector over here, at the position of the detector, you will just see the interfered pattern. You just sum these two. If they interfere constructively, you will see some signal. If they see destructively, you won't see any signal. Now, how does that depend on theta? Well, the only thing you can actually change over here is theta. Well, whether they interfere destructively or constructively will depend on the difference in their path lengths. Each ray travels a different distance. Well, this ray just travels up to this layer and is scattered. The other one travels further and is scattered. And their difference, well, you see, if you just draw these lines, the difference of their path, of the length of their path, is just the sum of these two sides. Well, they are equal, since the ray is coming at an angle theta and is being reflected at the same angle. So this length is d. This is 90 degrees. So this angle over here is also theta. This length is just d times cosine theta. And the path difference is twice d times cosine theta, because this is d times cosine theta, that is d times cosine theta. So the total path difference is 2 times d times cosine theta. And if this is just lambda, you get a constructive interference. Or if you are looking for a destructive interference, just put lambda over 2. So this basically tells you a way to determine lambda. You just measure theta. If you know what d is, you can just find lambda.
Looks like interference in thin films. Looks like interference in thin films.
Yes, exactly. Basically, it's the same idea. But you see, in this crystallography, you will have different values of d also. You see, this is a layer also. This is a layer. There is another layer over here. And the separation between these two layers are different. So if given a crystal, it doesn't have just a single layered structure. You can describe the same crystal in terms of different layers. At least this will give us a way to determine the wavelength and hence establish that we are actually creating X-rays. The wavelength. Well, you see, this tells us that that equation just gives me a single point for a given value of, at this point. But there's always these spreads, uncertainties. And furthermore, if you consider the energies, we are sending photons with energies of kiloelectron volts. The electrons inside have energies of the order of just electron volts. You can liberate them completely, but then there won't be any interference pattern. Or they just scatter off the nuclei, and then you see the pattern. The changes due to the electrons will be very small. Well, everything we do until the day before the exam. Okay, so see you on Monday.